Hello everyone, welcome to Understanding Physics, in which I'll try to guide you through understanding physics. So today on General Physics 2, we want to start to talk about alternating currents, or pretty much AC circuits in general. So before we get started, please consider subscribing as well as liking the video, and also please check the notes in the description to get the notes in this entire discussion. So now let's actually discuss about AC currents and DC currents. So DC is in which it is where your current is always within a single direction. Normally it is a constant. But for AC currents, it is alternating, in which it is pretty much it is periodic. So what are the ways for us to describe a AC circuit? So the most general idea is by using sine waves, because if you have already taken calculus or maybe even into differential equations or even signals, you know something about the Fourier series, in which you could construct any periodic function in terms of sines as well as cosines. So in here, I'll just describe this to be cosine omega t. Or, you know what, in here, I'll just describe this as sine omega t plus phi. And then there is this, and then there's the amplitude, which I will denote this to be the voltage. So the voltage is the amplitude Vp, as well as the frequency omega, for pretty much omega is the angular frequency. And then you have phi, which is the phase difference. So something that I want to remind you is that frequency as well as angular frequency can be related as 2 pi f. So angular frequency is 2 pi f. So this is very useful if you're trying to convert your frequency into something that you could analyze in a much more easier fashion. And not only that, I also want to discuss a little bit about something which you call as the root mean square. So what's the root mean square exactly? So the root mean square is pretty much a way for you to describe an average. And the way that you describe this average is by taking the square root of the average of the function squared. So this is what you call as the root mean square. So let's just do an example of this. So let's just say that I want to figure out what's the root mean square of this sine function. So the way that we'll do this is by actually first figuring out what is the v square. So it's Vp squared sine squared omega t plus phi. This is the square of our voltage. And so now we could now try to ask, what's the average of this function? So let's discuss a little bit about probability as well as statistics. So within statistics, if you have, let's say, a table in which you have, let's say, on average, there's like 19, 20, 21, 22. Let's say this is age. And then we could have frequency, let's say. Or pretty much the amount of people who has this age. And let's say it's 5, 6, 7, 4. And we want to figure out what's the average age. So the way that you could do this is actually just by summing it up. So 5 times 19 plus 20 times 6 plus 21 times 7 plus 22 times 4, divide everything by the frequency. So 5 plus 6 plus 7 plus 4. And this will later obtain the average age. So if you write this in a much more intelligible way, you could write this as the sum of the age, which is our function, as well as our n's, which is our frequency. So we could divide this by the sum of the frequency. So it's the total amount of number. So it's the total amount of sample is at the bottom, and then the top one is your function multiplied that by the amount of people who has that age. So this is the idea when you're taking average. And so now if we try to implement this into a function, let's say something like this, and let's just do the sine squared, let's say. We could have each slice here. So there are slices within. So there's sorry. So within the sine squared function, you could chop it up into multiple slices. Something like this. And then you could take what's the average height, let's say. So this will be, let's say, your age, let's say. And then what about the frequency? Well, let's just say that each of these has a frequency of 1 because we're just summing up each of these points. So it's the same thing as we are summing it by 1. So we can write this as the sum of the function. So this is our function instead. So it's the sum of the function. Multiply that by 1 for values from I equals to somewhere until somewhere. Now, to get the average, technically, this is not actually multiply that by 1, but instead you multiply it by the small change of x, which is in between these two. So the idea is that you're summing all of the areas together to obtain your top part here, which is the average, multiply that by the sample size. And so you could divide this later by the sum of the sample size. So it could also be written as something like this. Now, if you take the limit for delta x going nearer to 0, but also remember, because in here what I'll state with n will be dependent on which position will I denote as my final position. This would turn into the integral of function dx over integral dx. So this is the idea of how do you take averages. So we could now implement this into our sine squared function. So if we try to compute what's the expected value or the average, this will be Vp squared, the integral of sine squared omega t, which it turns out that it is the integral of 1 minus 2 cosine 2 omega t plus 2 phi over 2, divide that by the integral of dx from one point to another. Now, because this is a periodic function, we could just state that this limit is from 0 to 2 pi omega. And why 2 pi omega exactly? So 2 pi omega represents one cycle. So that's why we use 2 pi over omega. Now, this will later simplify into Vp squared, and then the half, this will be multiplied by half times 2 pi over omega. And then what about the cosine omega t plus 2 phi? If you integrate that, it will be some form of a sine 2 omega t plus 2 phi. And if you put in 2 pi over omega and 0, it's the same value. So the cosine part will later go to 0. That means that we'll get something like this, which means the expected value is Vp squared over 2. Now that's only for the expected value or the average of V squared. But what we want to find is the RMS. So we just need to take the square root of this value to get our RMS, which turns out to be Vp over square root 2. You could do the same thing for current. The IRMS will later be Ip over square root of 2. Now, Now, different functions or different signals corresponds to different RMS depending on the peak relations. So this is where you could actually say, like, pretty much on average the voltage will be around this value, and it gives a pretty good approximation of the power. So now I want to discuss a little bit about the circuit elements within a AC circuit. But before I get there, I want to introduce a small concept within mathematics in which we will deal with complex numbers. So the idea of complex numbers is that I equals to the square root of -1. This is the idea in which you take this value, the square root of -1, which you normally don't know, you instead denote that into one value. And something interesting to state is that there is a relation e to the power of I omega t is cosine omega t plus I sine omega t. This is a relation which you could actually derive from the Taylor series, but I won't fully discuss it here because this is a very abstract idea. So I'll just introduce this as a concept. And sometimes if you read electrical engineering books, the I is normally swapped with a J. So J is also a imaginary number. So why do I want to introduce this concept first? So the idea is that you could actually only look at the real part of this complex number, in which it could represent your actual model or your physical object. So let's say if you are supplying it with a sinusoidal wave, you could describe it as something like this, and then you could just neglect the imaginary part. But the imaginary part is pretty important when you're dealing with AC circuits, which you will later see when we will actually discuss about AC circuits. So let's jump into that. So within AC circuits, there are three things which you normally talk about: resistors, capacitance, as well as inductance. So let's discuss each of these components. So first, the resistor has a property in which the V over I is our resistance. So you could say that I equals to V over R. And if you try to put it, let's say that we'll just put a voltage in here to be e to the power of I omega t times Vp. So this will be the same thing as Vp cosine omega t. So we'll later just put these two values in just to see if these two are the same idea. So let's just plug it in. The function of I will be Vp over R cosine omega t. So what we see is that the I peak is Vp over R. And then they have the same phase. So what we see here is that it's pretty much just a change with the amplitude. From voltage, it turns into ampere with the proportionality constant to be ohms. And now this thing here, Vp over R, can normally be described as Vp over XR. So XR describes the reactance, or pretty much the resistance in terms of frequency. And this only works when you're dealing with the peaks. But when you're dealing with the actual function, like this guy, this is normally described with a Z, which represents inductance. So it turns out that XR and ZR is the same in here, which is the resistance. So So there's nothing surprising, it's just a change of name. But we'll see the influence when we start to deal with the other elements. But as for the sanity check, we could just actually try to put the complex number into our function. So this will be IT is the same thing as Vp over R e to the power of I omega t, which turns out to be the real component. So cosine omega t is the real component of the e to the power of I omega t. So it turns out that these two things are the same. Great. Now let's go a little bit deeper. So what about capacitors? So capacitor is described to be I equals to C dV over dt. Well, luckily we can put the voltage in first. Now this will separate into two different things. So IT will be described, let's just first use the cosine omega t. This will be negative CVP omega sine omega t. Now, if we try to reconstruct this, notice that cosine omega t could be written as cosine. Sorry. So instead, let's write it like this. Cosine A plus B is the same thing as cosine A cosine B minus sine A sine B. So now instead of A, we could use omega t, and cosine B, we'll just write that as phi. Now, for this value, we see that there's a sine omega t, which means that the cosine phi should be 0. So there could only be two values. It's between negative pi over 2 or pi over 2. But the sine b should be positive or 1. So it has to be pi over 2. So this could be written as cosine omega t plus phi. And this equals to omega c Vp. So if we try to look at the peak, it is as if that we get something like this. So what we get for the reactance is 1 over omega c. But the reactance in itself couldn't truly describe about the phase change. So instead we could just use a tool from complex numbers. But in here I want to sketch a little bit about the graph. So if we try to plot this within a graph, we can put cosine, something like this, and then the negative sign will go somewhere like this. Oh, yeah, something like that. So this is our current, this is our voltage. So what we see is that, so let's just use a different color. There we go. So what we see here is that there's a change of the phase, and it turns out that the current is lagging behind. Oh, sorry, it's not technically lagging behind here because the time is going in this direction. So if we try to take a scan of like between each time, it is as if the current is on its peak first before the voltage. So what we see is that the current is leading. So that's why we could see a positive pi over 2 here. So this is pi over 2. So there's this pi over 2 in which that the current is moving in front of our voltage. So this is interesting. Now what if we try to describe this using the complex number? Is it the same thing? So let's try to do it. Our IT will become C times I omega Vp e to the power of I omega t. And this is the same thing as writing this as Vp over 1 over I c omega, e to the power of I omega t. Now let's actually try to convert this e to the power of I omega t into the sign. So I e to the power of I omega t, if you use the definition from earlier, you could get negative sine omega t plus I cosine omega t. So this is the component of the sine omega t, well, pretty much the negative sine omega t. So that's why you could collect them all into I omega t, which is the same thing as the one that you have wrote. And taking the I over v, this value is, oh wait, is it? No, sorry. The v over I, we would obtain this to be 1 over I c omega, or 1 over I omega c. And from this, you could see that there is this imaginary part, which describes about the lag. But I will later try to discuss about how much is the lag based on the complex number later on. So now I just want you to accept that the inductance is 1 over I c omega, and this is related to the pi over 2 phase difference. So finally, let's talk about inductors. So inductors has V equals to L di over dt. Putting in the voltage, Vp e to the power of I omega t, this would equal to L di over dt. Now let's try to find what the current is. So this will be Vp over L omega I at the bottom, and this is e to the power of I omega t. So we could just check the value, just plug it in, and it turns out that it's the same thing. Oh wait, sorry. This is for the complex number. So this is what we get if we use complex numbers. But what about the normal numbers that we normally use? So this will be Vp cosine omega t equals to L di over dt. Solving the differential equation, you would get the I to be Vp over omega L sine omega t. So what we see here is that we got 1 over I e to the power of I omega t, and its relation is sine omega t minus I cosine omega t. So what we get is the same thing in here. So this is the real part. Same idea with the previous one. And so what we get from here is that the peak would be Vp over omega L, which means our reactance will be omega L. But we could also rewrite this as Vp over omega L cosine omega t minus pi over 2, using the same logic as previously, in which you will use the cosine a plus b. And this in turn tells you that the current lags, I lags by 90 degrees, or pi over 2. But if you look at this from the inductance, no, sorry, if you look at it from the complex number, you would figure out that the inductance will be I omega L. So it turns out that there's a relation between this inductance as well as the lag. But what is it? So before we get there, there is a diagram in which I want to try to introduce to you, which is called as the Phasor diagram. So the idea of a Phasor diagram is it's pretty much like a polar. It is pretty much a polar coordinate in which you would have your amplitude as well as your omega t. And so this might be your first function, and then you might have another function which you'll call as B as the peak, and then there's this difference which you call as phi. This is what is drawn within a phasor diagram. So this helps you to visualize which one is leading, which one is lagging, and whatsoever. You could plot it as long as you know the function of your current and your voltage. So I want to describe one type of a circuit in which it involves an AC current. So it is called as the LC circuit. So it's something like this. It's pretty simple, but instead of the initial conditions to all be 0, let's just say that the capacitor has some charge. And let's see what will happen. So we could just do this in the Kirchhoff way. We'll just denote positive and negative, and let's say current is going in this direction, even though it's going back and forth. So what we will get from Kirchhoff's law is the voltage difference, so the voltage of C plus the voltage in between the inductor, which is LdI over dt equals to 0. So let's actually take the derivative. So anyways, this is by assuming that the magnetic flux through the circuit is negligible. So we can just do this. So what we could get is the dVc over dt, which is pretty much the current, yeah. So C dVc over dt is current. So this is I over C plus L d squared I over dt squared equals to 0. Now, this is based on general physics 1 idea of oscillation as well as the differential equation. So I won't fully discuss how do you solve this type of differential equation again. So based on general physics 1, the way that I do it was by using the cosine as a guess. But in here, I want to use a much more electrical engineering way. So we'll use the characteristic polynomials again. So we'll obtain 1 plus CL s squared equals to 0. So this would obtain the s to be plus or minus I to the square root of LC. 1 over the square root of LC. So I'll just take the positive side. So we'll get e to the power of I over the square root of LC. Multiply that by A, in which A is a complex number, let's say. So this describes pretty much a cosine t, so it's IT over square root LC. So it's A times cosine t over the square root of LC plus phi, or the phase difference. And so you could actually have any type of A as well as any type of phi to be the solution of this problem. It turns out that A and phi are both independent, thanks to a second order differential equation. And so something that I want to point out in here is something which you call as the oscillation frequency, or the natural frequency in here, which is 1 over the square root of LC. This value determines how fast is the oscillation, and this will later be related to damping. So instead of only having a LC circuit, we could do RLC. So it's something like this. And we'll do the same computation as before. So we could just put, let's say, this current to be I. We'll do Kirchhoff's law. It's VC plus IR plus LdI over dt. It turns out this is I over C plus RdI over dt plus Ld squared I over dt squared equals to 0. Now the way that you would actually solve this equation is also by using the same idea. We could guess the solution, or maybe from the real world perspective, it is assumed by using characteristic polynomials and then figuring out if it is a underdamped, overdamped, or critically damped. So that's what we'll actually do. So we could just solve this. Let's actually make this into a characteristic polynomial. Let's multiply everything by 1 over L first. So we will get 1 over LC plus R over L S, which is our variable in this case, plus S squared equals to 0. So we can solve the characteristic polynomial straight away by using the quadratic formula. So this will be S equals to the negative R over L plus or minus the square root of R over L squared minus 4 over LC over 2. Now you could simplify this further just by multiplying the top and the bottom by L. So you could get negative R plus or minus the square root of R squared minus 4L over C. Divide that by 2L. Now remembering about the idea of discriminants, you could also determine what's the solution to your polynomial, to your characteristic polynomial. So there is overdamped, underdamped, as well as critically damped. So for a overdamped solution, it will be the R squared will be greater than the 2 square root of, the R is greater than the 2 times the square root of L over C. And this condition is applied for other conditions as well, depending on the inequality. So let's take this idea back from General Physics 1, in which you could actually get the solution of the overdamped solution to be a e to the power of s plus t plus b e to the power of s minus t. So this s plus and this s minus corresponds to two different solutions of the characteristic polynomial. For the critically damped, it will be e to the power of st. Multiply that by a linear equation. And especially here, if you actually try to plug in r equals to 2 to the square root of L over C, what you get is e to the power of negative RT over 2L. Multiply this by the linear equation. And for the underdamped, what you would get is a times cosine of the st. I'll just write this as omega t plus phi, in which your omega will be the square root of 4L over C minus R squared over 2L. And this will equal to, and this thing is multiplied by e to the power of negative R over 2L. T. So remembering about the shape, for the overdamped solution, it will be dwindling straight away. For the critically damped, it is having one cross-section before going to 0. And for underdamped, it's pretty much a oscillation dwindling down. So we have already discussed about this RLC circuit as well as its solutions. So now let's go into a driven RLC circuit. So same idea, you get resistor, inductance as well as capacitance, and then you could solve for the differential equation, which I'll just write because in the end it is still similar to the previous examples. So it's I over C plus R di over dt plus L d squared I over dt squared, and this equals to the voltage. And particularly it's the derivative of the voltage, because when we actually obtain this differential equation, we do it by taking the derivative first. So this is why we have the derivative of the v. And now the solution of the derivative of v, and so let's just say the v here is vp cosine omega t, or e to the power of I omega t, just to make this simple. So the derivative here will be I omega vp e to the power of I omega t. So solving for this differential equation might be a little bit complex, because there is the particular solution as well as the homogeneous solution. But the fact is, if we want to only analyze this when time goes to a very big number in which the homogeneous solution dies off, instead what we will get is only the particular solution. So we could actually try to determine what's the particular solution then. So let's try to do this. So the first idea is, let's just actually guess for a solution which doesn't dwindles down. And one good example of this is a harmonic solution. So we could just state A e to the power of I omega t is my solution for I. So technically A is the I peak. And we'll just figure out what's the I peak with respect to all of these variables. So if we write it down, we could get a e to the power of I omega t over c plus I omega r a e to the power of I omega t plus negative omega squared L a e to the power of I omega t equals to I omega vp e to the power of I omega t. Now something to notice in here, which is not really visible if you're doing this with real numbers, is that you could actually cross out all of the e to the power of I omega t. And this is because of the modulus, or the absolute value of e to the power of I omega t will always be 1. So it's not 0. So we could just cross the entire thing out. And then after that, we could actually collect all of the terms together. We could get a 1 over c plus I omega minus omega squared L equals to I omega vp. So we are able to figure out what is the A, or the amplitude, which is I omega vp over 1 over c plus I omega minus omega squared L. And this could actually be simplified much more further. Oh, sorry, that's I omega r. So maybe an easy idea to extract some more information from this is to get this equaling to IP, or the peak of the current. And let's see where it will lead us towards. So pretty much this IP is applicable for the real value technically, because we are not dealing with the imaginary number. But the idea is that taking the modulus of a complex number could be separated out as something like this. So you could just figure out the absolute value of the magnitude, as well as the absolute value of the cosine, which is normally 1. So this is as if that we will write it like this. The absolute value of I, no, sorry. So we'll just figure out what is A first in order to figure out what's the absolute value of the I, or in which we could be able to determine what's the peak. So an easy way to simplify about this is that we could actually divide the top and the bottom by I omega. This will obtain Vp over R minus omega squared L plus 1 over C, all of them divided by I omega. So this will simplify much more further into Vp over R plus this will be I omega L minus 1 over I omega C. Now this is something very interesting. This value here is actually Vp over the sum of all of the inductance. No, sorry, yeah, inductance. So it's not X, it's Z. Zn. So this brings up a very interesting fact, is that if you put elements within series, the inductance is pretty much very similar to the resistor, in which you could just sum them all up. And this is also true when you're dealing with parallel. Sorry, this should be positive. So we have obtained this. So let's actually try to figure out, what about if we take the absolute value of this A? And so remembering our property, you could just take the modulus of both of the products, technically. So it's the absolute value of the Vp as well as the absolute value of the denominator. And so what you'll get is, this is Vp and this is Ip. Multiply this by the bottom side here, which is 1 over the square root of R squared plus that's xc, and then that's xc and xl. So what you'll get is, it's the omega L minus 1 over omega C, everything squared. So if I haven't really mentioned about taking the absolute value of a complex number, the easy way to visualize about this is by actually trying to figure out the length of a vector within the complex plane. So we got the real as well as the imaginary. So if you have this be A and B, this is AB plus I, and the length is the square root of A squared plus B squared. So that's the idea. And this bottom side here is pretty much also the inductance. It's the absolute value of the inductance. So the relation between this A as well as the IP is very closely related. But something that you might actually ask to yourself is, what about the phase difference? Is it additive? Is it subtractive? Or maybe even multiplicative? The answer is no. And the key idea into understanding the phase difference is by using complex numbers. So here's the idea. If you have A plus BI and then you want to figure out what's the phase difference, this angle here is the phase difference. So to figure out what the phi is, you could just use simple trigonometry. So it's B over A. Or pretty much the value that you get from the imaginary part over the value from the real part. So the value in here will be omega L minus 1 over omega C, divide that by the resistance, or XL minus XC over R. And this is the tangent of phi. So you could figure out what's the phi thanks to the imaginary plane. So you could use this idea as well when you're dealing with the with a inductor system only or a capacitor system only. And the relation will later give you a lag of pi over 2 or a leading factor of pi over 2. To end the discussion with an AC circuit, I want to describe about power. So so how do we describe power when we're dealing with AC circuit? Because the power is always fluctuating. Now, this is the idea in which we could also use statistics in order to determine what's the average power. So let's do something like this. Let's just take power to be I times V, which is something in which we have already figured out from the very start. And now what we want to do is to take the average of this. And let's just state that the I has a phase difference. So this will be IP sine omega t plus phi. So pretty much sine and cosine could be swapped any way that I want. Multiply this by the Vp sine omega t. Now let's try to figure out what's the average. So first, sine omega t plus phi has a property in which it is sine omega t cosine phi times cosine phi plus the cosine of omega t plus sine phi times sine phi. So we could just open this straight away and also remember that IP and VP is a constant. That means that if you take the average, it will just affect the average by linearly. So it will be IP times VP at the front, and the average of sine omega t squared cosine phi plus sine omega t cosine omega t sine phi. And now we want to figure out the average. So another thing when we're dealing about average or expected values is it is also linear. So we could just separate this into two. Sine squared omega t times cosine phi plus the average of sine omega t cosine omega t sine phi. Now, we have already figured out what's the average of sine squared omega t, in which it is 1/2. We have already derived about this early on when we did RMS. And now what about the value of sine omega t cosine omega d, or omega t? So we could just put this into our formula. So it's from 0 to 2 pi over omega sine omega t cosine omega t dt over 2 pi over omega. What we can do is that we could just use substitution, let's say. So it's sine omega t equals to u. So omega cosine omega t is du dt. So this will be the du over omega times u, the integral from 0 until 0. Now this is where it gets interesting, because the integral itself is pretty much simple, but also the boundary is from one value to the same other value. So this will later lead to 0, in which in the end your average will turn out to be 0. So this value turns out to be 0. So what you get is IP Vp over 2 times cosine phi. Now, to make this much more interesting, we could just rewrite this as IP over the square root of 2 times Vp over the square root of 2 times cosine phi. Now, what we get here is that these are actually the RMS. So it's IRMS multiplied by the VRMS equals to the cosine phi. Now we know that this is pretty much what we call as the power, and it turns out that you could just use the RMS to determine the average power. But also you need to also remember about the phase difference, or which is something which we will call as the power factor. So something to state in addition to the power factor, or pretty much power, is the transformer. So the transformer is an idea in which that you could transfer power from one place to another. So let's actually try to derive the transformer. So the idea of a transformer is that you would have a coil, and then this coil is going to produce a magnetic field, which will later be induced into this other coil. So the idea is that based on Faraday's law, the change in the magnetic flux is related to the EMF. And this is only for one loop. You could do this for multiple loops depending on your magnetic flux anyways. So pretty much the idea is that if we have a constant magnetic flux, this will later equal to the number, this will be related to voltage over N. So the voltage in between these 2 points. And this is also true for the other side. So the voltage over N must be constant. And now this is why you could get V1 over N1 equals to V2 over N2. Or a much more easier way to write this, V1 over V2 equals to the N1 over N2. So N in here corresponds to the number of coils, if I haven't already mentioned about this. Now this is a weird idea in which, how could you transform the voltage just by adding nothing into it? It turns out that you would need to sacrifice something else, which is going to be current. So you couldn't truly create a ideal transformer anyways. I mean if you have, let's say, a perfect material which could contain all of the flux, you would still need the current just to transform from one energy to the other. So we're not breaking any thermodynamic laws in this case. Finally, I want to describe about how do you transform a AC circuit into a DC circuit. No, sorry. A AC current into a DC current. So let's think of an idea of doing this. So you want to transform this wave-like motion into something in which it is static. So there are multiple ideas of this. One idea is to use a diode. So what exactly is a diode? So remember a while back in which I discussed a little bit about diodes? Diodes are pretty much a one-way gate that it allows only current passing through only one direction. So if you have a AC current flowing in this direction, it will later become something like this. It's like gonna jump. So it is pretty useful when you're trying to transform an AC into a DC. But this is not enough because it is like it's still just bouncing. So it's like going like this. So there's like a clock, you could say. So instead, what you could do is to actually extend each of the peaks. And the way for you to extend these peaks is simply by using a RC circuit. So if you attach a diode and then you connect it to a RC circuit, something like this. So if you actually apply a AC current, AC voltage at the top, it will it will cut out everything that is going negative, and then by using the RC circuit, it is gonna make the wave into a much more stable type of current. Well, it is not directly straight, but you get the idea that it is much more uniform compared that to before. So another type of interesting circuit is a filter in which you could use a capacitor as well as a resistor, and then you put it in a certain way to select certain frequencies. And this analysis could be done by taking the inductance, but I won't fully discuss it here. So if you want me discussing about filters, you could leave it in the comment for me to describe in a much more fully extended manner. So that's all for this video. So thank you very much for watching, and if you want more of these videos, please consider subscribing as well as liking the video, and also please share this to your friends who needs to understand physics in a much more deeper understanding. So thank you very much, and I will see you on the next video.